So now in this example, example 2.2, we're dealing with a straight line system in which we have a particle that has a mass m that has a force f of x applied to the particle moving in the straight line. And we've also said that x increases to the right and decreases as it moves left back toward the origin. Now in this example, we're going to find the equation of motion and solve for the state of the system in which it has a constant force f of x that's applied to the particle. And so when we insert this into Newton's second law, this is our law of mechanics, we get that f of x is equal to m x double dot. So this is our laws of mechanics. We make this into an equation of motion, which is a second order differential equation. X double dot is equal to f of x divided by m. And now we'll integrate both sides with respect to time, and then from this we'll get x dot as a function of time plus our first constant of integration is equal to the force, that constant force f sub x, divided by m. And then when we integrate the right side, we're multiplying by t because f of x over m is a constant. It's a constant force and then a constant mass of the particle. And so one thing we can see quickly with this equation is that the speed, x dot, isn't going to be constant. It's going to vary with time, and then it's also going to have an initial speed at which it starts. And so we'll take care of this with a boundary condition, which is that at time is equal to 0, x dot t is equal to x dot at that time 0. And so when we apply this, we get the general expression for our state, which is x dot t is equal to an initial speed plus the force that's being applied to the particle. Remember, this is a constant force multiplied times t. And so this gives us the general expression for the speed of the particle when a constant force is being applied. And now to solve for position, we have dx dt is equal to the expression we have for our speed, which is our initial speed plus the constant fx over m multiplied times t. We use our separation of variables, and with this distribute the dt on the expression on the right hand side, and then we'll integrate both sides. And after integrating, we get this expression where we have that the position as a function of time plus a second time constant is equal to the initial speed multiplied times time plus our constant, which is the force divided by the mass, and then multiplied by t squared divided by 2. And I just noticed that I made a mistake in this expression, so we need to add a t. This is fx over mt dt, and by integrating, that's where we get our t squared over 2. And so we still need to get rid of this second constant of integration, and to do that we'll apply the boundary position or boundary condition on position, which says that at time is equal to 0, the position is equal to the initial position. We'll make these substitutions in which we have, this is the position at time 0. Here t is equal to 0, so that term goes to 0. And then here t is equal to 0, so the t squared also goes to 0. And so we get from this that c2 is equal to negative x at time 0. And we plug all this in and rearrange our terms, and we get the general expression for position as a function of time is equal to an initial position at time 0 plus an initial speed at time 0 multiplied times t plus our constant fx f sub x over m multiplied times t squared. And so now we have a scalar expression that is one part of the solution. It's the solution for the position, and then here's our solution for our speed that came from our original second order differential equation, which was x double dot is equal to the constant, the force in the x direction divided by the mass. And these are scalar equations for a particle that's undergoing a constant acceleration.